So, all right, guys, welcome back. You remember that on our previous lecture, we covered number representation systems, the floating system, the standard representation system, and we concluded that numbers that have finite expansion in one system can have infinite expansion in another system. And these number representation systems help us to be more efficient in representing big and small or very small numbers. And then the number that can be represented in exact form is called a machine number. So today, which is lecture 3, want to look at series expansions. So what is a series expansion? So let's motivate this. So if you use your calculator, you can actually be able to solve that expression 3 times 10 squared over 2x plus 4. You can solve that one. But how about if you want to compute the square root of 4.1? You know the square root of 4. So using Taylor expansion, you should be able to approximate the square root of what? Of 4.1 from the square root of 4. Similarly, if you are given sine of 0.6, sine of 0.6, you can actually use the definition of trig, because you know that sine is equals to what? Sine is equals to opposite over hypotenuse. So sine of 0.6 will be opposited over hypotenuse. So what we are then interested is to finding these two variables, your A and B. So in this course, remember that all angles will be in radians unless or stated otherwise. So the Taylor series expansion of function f of x at a point A, about that point, is given by f of A plus f prime of A x minus 1. So it starts with f of A, and then we have for the first derivative evaluated at that point A multiplied by x minus A plus second derivative evaluated at the point of rotation, which is A, over 2 factorial x minus 1 squared. You square that. And then the third term will be third derivative is also over 3 factorial times x minus A. This is also cubed. So cubed. So take note of the increase in those values. So the generalized form, this one can be written as the summation from k is equals to 0 of 1 k factorial derivative of k evaluated at a x minus a to the power k. So if the series converges, you expect that f of x should be equal to the Taylor series expansion, which is given by that formula. And then the Maclaurin series is a special case of the Taylor series. This has got a center of expansion, A being equal to 0. So the Maclaurin series expansion for f of x will be, we are now evaluating at A, so this will be f of A, which is f of 0, first derivative evaluated at 0. This is what? X minus A, but A is 0, so this will be x. And then this will be second derivative evaluated at 0 divided by 2 factorial, then x minus a, but a is equals to 0 squared, so this will be x squared and so on. So this converges if f of x is equals to the summand from k is equals to 0 up to infinity of 1 over k factorial fk derivative evaluated at 0 x to the power k. Let's look into some examples. So if you want to obtain the Maclaurin series expansion of f of x, which is given by e to x, you need to find the derivatives of this function. So if you are given f of x, you differentiate it, find the first derivative, you also get f of x. Find the second derivative, you differentiate the first derivative, you get e to x. And then for the k derivative with e to x, it doesn't change. Make sure you go back and revise your differentiation. Make sure you know the derivative of ex, sine x, ln x, square root of rational functions, and so on. And then you need to evaluate these at a is equals to 0. So f of x will give you e to 0, which is 1. Any number raised to the 0 is 1. F of prime, again, you substitute for x by 0. This will give you f of prime 0 is 1. Second derivative, you substitute here by 0x, you also get 1. For k derivative, you also get 1. So the Maclaurin series of e to the x, Maclaurin series of e to the x will be given by, we are now summing, will be given by f of 0. Remember, it's f of 0, which is what? 1 plus f of first derivative evaluated at 0 times x, which is equals to first derivative is what? 1 times x, which is x. Second derivative plus second derivative, which is 1 times x squared divided by 2 factorial plus third derivative, which is 1 times x cubed, which is x cubed divided by 3 factorial plus and so on. And this expansion converges for the modulus of x less than infinity. So there's something interesting about this expansion that I want us to notice. So you see those graphs? Maybe let's write down this expansion. Let's write down this expansion for e to x. So this will be 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Right, so I want to show you what happens if you increase the number of terms in your expansion. Alright, so I hope by now you have noted that expansion there. This is 1 plus x squared over 2 plus x cubed over 6. So we want to plot this and see what happens if we increase the number of terms into our graph. So I'm using Mathematica to come up with the plots. So let's first of all plot the graph of e to x and see what happens from -1 to 1. Sorry, I made a mistake. Don't do that. So if you make a mistake with this, sometimes copying plot range, plot ex Ex of x, not exponent of x x minus 1 to 1. Now it's fine. So this is your graph of e to x. It's an exponential curve. So coming back to this expansion, so if I pick these two and check how will they look like in our graph. So let's pick 1 plus x. Let's plot that and see what happens. So if I plot e to x together with 1 plus x, you see, now I've got this curve, my curve e to x, and then I've got this line 1 plus x. And then the questions that you should ask yourself is this line a true representation of this curve e to x? Maybe, I don't know. Let's check. If I increase, if I plot, if I increase and put another and consider another term. So if I consider this one as well, x squared over 2, what happens to the graph? If I consider 1 over 2, what happens to the graph? X squared over 2. So let me plot this one and 1 plus x plus plus x squared over 2. So you should see something there. So first you have got this blue line, which is our curve. So if I increase another term from 1 plus x, I get this orange curve, and this orange curve looks similar to be a better approximation to our e to x. So this tells us that as we increase the number of terms in our expansion, it becomes more accurate. But above all, as we increase the number of terms in our expansion, this expansion will converge. So the expansion will converge at some point, as you saw from the previous example. How about the Maclaurin series for f of x is equals to sine x? If you differentiate sine x, you get cos x. If you differentiate cos x, you get minus sine x. If you differentiate minus sine x, you get minus cos x. Evaluating this at 0, you get 0, 1, 0, minus 1. Remember that when you're evaluating these tricks, your calculator should be always in radians mode. Otherwise, you run into mistakes there. Therefore, the Maclaurin series expansion for this one is f of x, which is 0 plus 1 times x plus 0 times x squared 0 plus 1 minus 1 x times x cubed over 2 factorial and so on. So that will be the the Maclaurin series for sine x. It's alternating, as you can see, from 0, 1, 0, minus 1, 0, 1, 0, minus 1. So that's what you get for expansion of that one. And if you sketch it, this is what you get. So sine x is this red curve, represented by this red curve. And then the first expansion, the first term in your expansion is x, so x will give you a straight line, which is a far much worse representation or estimate of your curve sine x. If you continue, you get x minus x cubed plus over x3 factorial, which is something that can be used to represent, but as you add more terms into that expansion, you get a more accurate expansion. You get a more accurate diagram. So you can go through this example in your spare time and satisfy yourself that the expansion for 1 over 1 minus x is that one. Okay, thank you.